So I'm Nachi, and I'm from Chalmers, and I'm a PhD student. I've done this work together with Fabian and Carlos, who are also PhD students. Carlos is right there. So it is our first ICFP paper. So the distinguished paper was a very sort of warm welcome into the community. So thank you for that. And I'm supervised by Alejandro Russo. I do not imagine that's an easy job, but anyway, let me get to the point. So normalization for Fitch-Style Modal Calculi. So the first question here is what on earth is a modality, right? So it's a fairly broad notion that we're looking at here. So what I do know here is at the least a modality is a type former with some properties and operations, right? This is what I mean in this talk by modality. And we're going to commit to a special class of modalities, in specific the necessity modality. And the operations that this modality is equipped with is the so-called necessitation rule, which says if you have a closed value or a closed term, which is basically a way of saying you don't have any free variables in your term of type A, then you can box it up as a term of type box A. And you also have the so-called axiom K, which says if you have a box function, you have a box argument, you can squash them together and you get a box result. So of course, these operations in themselves are pretty, this is the basic foundation that we commit to, but they're not enough, right? We want richer operations, but this also depends on the application of interest, right? This box, it depends on how we interpret this box. So there's many ways we can interpret it. One way is to think of it as an impure value, as a pure value in an impure language, or you can think of it as a secret value in the context of information flow control. You can think of it as code or dynamic value of type A in the context of stage computation or partial evaluation. So, and of course, each of these applications demand different operations, right? You don't always want the same kind of operation. For example, here's the so-called axiom T, which is basically in our sort of type propositions as types interpretation. It's an operation which takes a value of type box A to A. You don't want this if you want box A to mean secret, right? This is basically saying leak the secret. You don't want that. So it really is the question here is what are the operations that you're interested in? And sometimes you're interested in different things. And if you want to mix and match them, you end up in different systems of interest, right? Different logics correspond to different lambda calculi. So we have to study these different systems in isolation, not necessarily separately, somewhat together, but while respecting their differences. So today I'm going to talk about these four systems, but there may be systems beyond the four I'm going to talk about. But we're going to stick to these four for today. And the four are basically found by different combinations of these axioms or operations. And of course, I'm going to talk to you about normalization today. And then sort of the natural question here is why normalization? Why should anybody care about normalization? So there's a fundamental interest in normalization, right? So even if that doesn't sort of appeal to you, so the other way to look at it perhaps is you have this big equivalence class of terms. So, all these semantically equivalent, complicated terms. It's an infinite set of terms, right? So you want to crunch it down to one sort of canonical representative so that you can talk about this entire equivalence class using this one canonical representative, right? So this is why normalization matters, because instead of dealing with the noisy term syntax, you can now look at these little tiny normal forms, which are very well behaved. And you can prove a number of useful things using these normal forms, right? So in the paper, there's examples about, hey, look, you can prove capability safety, you can prove non-interference, binding time correctness, decidability, completeness, yada, yada, yada. There's a bunch of examples, you can have a look at them. And today the focus is not on normalization in general, right? It's about modal types in specific. So it's about constructs which allow you to construct and eliminate the modal type, so the box and unbox, that is. So and specific, we're going to look at a specific way of formulating modal calculi, the so-called Fitch-Style Modal Calculi, and they extend the notion of typing context with this new lock operator. So this lock operator can be thought of as this delimiting operator. So typically you have a list of variables in your context, but now you also have this lock kind of getting in the way. So it's separating your list into a sublists, right? And the four systems that I mentioned earlier has a uniform introduction rule, right? It says if you have a context with a lock in it, and this is a term of type A, you can construct a term of type box A by removing the lock from the context, right? So what's different about these systems, of course, is the elimination rule. So the four systems have four different elimination rules, and each of them have so this is where the lock really comes into play. So you use this lock to carefully formulate how this elimination rule should work. But before I go into the specifics, let's do a little bit of an experiment, right? So I want you to take a look at these rules, right? These rules in front of us, and now I want us to think about implementing substitution, right? So and when I say substitution, basically what I mean is I'm going to give you a list of terms for the variables in this term. And what you have to do is implement substitution for your term calculus. And I want you to implement the case for unbox, right? So, and if you look at this, what's going on is there's a lot of stuff going on. you're probably looking at this typing rules and going, how am I going to implement substitution for this? I have to slice and dice things. And at this point, if your brain is going, ah, that's exactly what I want. That's exactly where I want you, right? So hold on to that fear, and hopefully it will convince you it's a bit of a good idea that what we're doing, right? So the technical issues here are that there's repetitive and tedious syntactic reasoning, right? So you got to. So even if you may do it once, what will end up happening is that you say, okay, I'm happy to do this for one system, but then you have to sort of repeat this for each and every system of interest, right? So that's the problem here. And then it's difficult to mechanize normalization. The interest here is to implement normalization algorithms and verify them in a proof assistant. It's very difficult to say straightforward induction. You cannot do that anymore. So you have to sit and do the work yourself. And lock appears to be an ad hoc technical device, dry of intuition. One of the takeaways I hope you will get from today is that it's not. It has an elegant semantic interpretation and thus an intuition. And what we're going to do is we're not going to deal with syntax. We're going to do normalization in a sort of a semantic way. And in specific, we're going to do this by the technique called normalization by evaluation. And this technique has two critical components, right? So the first component is an evaluator, or an interpreter, which is a function, eval, which takes the terms in your language and interprets it into some suitable semantic domain, right? So these are open terms, so you have to think of the semantic values being functions, some kind of function, which takes a denotation or an interpretation of the context and produces an interpretation of the type. Code basically takes the exact same thing that eval produced and inverts it back to a syntax in normal form, right? The trick is, of course, in how do you actually implement them. But before we get there, just observe here that the normalization function, once you've implemented these two functions by doing all the hard work, the normalization function simply falls out just by composing them, right? So that's the main appeal here. So, but of course, the critical question when it comes to implementing NBE is always, what is the semantic domain? What is the interpretation of context? What is the interpretation of the types? And what is this fat arrow that I haven't told you what it is about, right? So this basically is asking the question of what are models of Fitch-Style lambda calculi, modal lambda calculi. So I'm going to tell you the story in two parts, right? So first, we're going to sort of demystify what this arrow is. We're going to identify the so-called possible world semantics of this Fitch-Style modal lambda calculi. And then the moment we've identified that, all we've got to do is pick parameters in these model specification, and you end up getting models, NBE models, for almost free, right? So that's how the story goes. So the possible world semantics is defined, or it can be thought of the following way, right? So we're going to interpret our terms in these so-called frames. So what is a frame? So if the frame, it basically has three components. It's a set of nodes. So in this case, I don't know if you can see that. So this W here basically is a set of worlds, right? These are the nodes in the graph. And so in between these worlds, you have two kinds of relation, Ri for intuitionistic accessibility and Rm for modal accessibility, right? So you have these two kinds of edges between these graphs, right? And how we're going to use these sort of graphs or frames is we're going to interpret the type box A as at a world W as the interpretation of A at V, where V is a modal successor of an intuitionistic successor of your original world, right? So this is the interpretation, but we'll get around to what exactly the intuition behind this is. The interesting bit is the interpretation of the base types and the function types and all the other types that you typically have remains the same, which can be, you can have a look at the paper if you're interested in that. So, but the interesting question here is perhaps, what is this interpretation of this curious lock? We interpret the context, the other stuff in the context the usual way, right, using products. But what do we do about lock? So for this, we need to sort of revisit the intuition of the box, right? So if you think about box as a statement about the future, right? I've ignored this sort of intuitionistic blue relation here because it is a reflexive relation. So for the time being, we can sort of ignore that. So if you can think of box as a statement of the future, where you say if box A holds at a world W, then A holds at a future V. If that's the intuition you're going for, then lock is an intuition about the past. It's a statement about the past, right? It's as if delta lock holds at a world W, then there exists a past world U where delta holds. So this is the basic intuition that lock is giving us. So, and this is what we're going to use for our interpretation, right? We're going to say delta lock holds at W. For it to hold at W, it means it holds at some past world U. So we're just going to write this down a bit formally. So, and once we've given the interpretation of a type, I must also give you terms models as well. And the possible world semantics actually gives us a very intuitive way of thinking of these terms, right? So the word Fitch-style comes from natural deduction in modal logic. And what happens over there, if you have a formula of type box A, you can open this sort of portal into the future, and you can import a value of type A in your future world, right? And in lambda calculus, this corresponds to an elimination rule, which says, if you have a term of type box A, you open this portal by marking that in the context, by adding a lock to the context, and then you get the term unbox T of type A, right? So this is how it's defined, but of course you might have seen some extra restrictions there. So just because you're in a future world doesn't mean you shouldn't make any further assumptions. That's why this restriction says, yeah, you can make further assumptions in this future world if you want. So there's an extra gamma prime sticking around after the lock. So that's the justification for one of the unbox elimination rules. And the introduction rule, or the corresponding export rule in natural deduction, says if you have a sort of so these boxes in natural deduction are called strict subordinate proofs. If you have this sort of portal to the future or strict subordinate proof, you can close it up and you can export any formula of type A outside as a box A. And in lambda calculus, this corresponds to an introduction rule, which says if you have a term of type A with a lock in the context, you remove the lock, close the portal, and then you get a term of type box A. This is the introduction rule for the calculus. And of course, the whole point of these sort of portals or strict subordinate proofs is that so you don't freely copy, formulas back and forth. That would, defeat the whole purpose of the box. So you cannot freely copy things. And this restriction is captured by the variable rule. The variable rule says you may refer to any variables to the right of the latest lock. So if there's anything to the left of a lock, which means it's in the past world, so you cannot refer to it. That's the idea. That's the restriction that the variable rule is baking in, right? So in light of, so that's the end of the possible world, the part one of the story. In light of the semantics that we've set up, what we're looking at now is the NP. So now we've sort of defined, unrolled the definition of the fat arrow, right? So now it basically says you interpret the term in a function for all worlds such that if given an interpretation of gamma, you give me an interpretation of A, right? So I've just instantiated the previous slide with the possible world semantics now. And normalization, of course, remains the same. And now the curious question is, we've defined in the possible semantics, which can be thought of as an interface, right? So now you have an interface, and now you want to instantiate the parameters of this interface so that you can get, I claim, a normalization algorithm, right? And we know just from existing literature for the simply type lambda calculus, you can achieve this by instantiating the set of worlds to context and the intuitionistic accessibility relation to order-preserving embeddings, which can also be defined in an almost the same way. And now, so the interesting question here is, what is this modal accessibility relation? And that's the only remaining bit for us to actually instantiate the interface. And using this evaluation function, I've given you intuition for how it's implemented. But the moment you pick the right modal parameter, modal accessibility relation, the quote function also falls out. I'm not going to show the implementation here, but it is in the implementation and the paper. So what is this relation is the question, is what we're after. And to understand this, I want to sort of recap the rules from before. So we had one introduction rule and a number of elimination rule, depends on the terms of interest. But look at these sort of rules, right? So if you see them, in all of them, something interesting is going on. So all of them are an extension. So if you look at the context below, it's an extension of the context above the line with some side constraints, right? All of them have this form, right? And we're simply going to say the context in the conclusion is in some relationship to the context in the premise, right? And we're just going to write this down, right? And the moment you write this down, you have this, with the possible world intuition, observe that this is basically saying, if you have a term of type box A, that is if box A holds in gamma, and if delta is a modal successor of gamma, that is if you have this arrow, this orange arrow to delta, and now you know that A must hold there, just because that's the definition of box A, right, in the model. So this is how we're going to read the unbox rule. So what this is basically saying is that now you can look at the syntax of the four calculi that we're dealing with, look at the relationship between the context in the conclusion and context in the premise, and use this to instantiate the modal parameter relation, modal accessibility relation. So, and that's exactly what we're going to do. We're going to say gamma is related to delta. For this is defined as the following. It says, delta can be factored as an extension of gamma with the log, gamma prime, and the side condition, which was thrown in before. We do the exact same thing for the other S4 system, where we say delta can be factored as an extension of gamma and gamma prime, right? So we're just sort of reading off from the syntax what this relationship is, and we get the corresponding modal accessibility relation. Now, to understand what is really going on, so observe that the modal accessibility relation here is both reflexive and transitive, which is the expected frame conditions in modal logic, right? So that's the reason all of this is really coming together expected frame conditions for the axioms T and 4. So, and you can do the exact same thing for the other two systems. It still works out. By works out, I mean you can implement quote by instantiating R in this way. So that's what I've been so far. I've been talking to you about these four systems, right? So far we have these sort of curious, T and 4 axiom, which gives you a kind of a co-monadic interface or some restrictions of it. Now it's also interesting to ask other questions like, oh, what is a Fitch-style applicative functor calculus? Can I recover normalization for applicative functors, monads, just from this general framework? What is so special about the calculi that we studied here? So there are questions you can ask beyond the specific axioms or operations that we studied today. And I think the road ahead is very exciting because then we start talking about return and join and the GL axiom. And there's also even further question one graph. What about interacting modalities? What about index modalities? The richer modalities you have, the more interesting your applications get. And this is also an open call for applications. So if you think, oh, look at I want these applications. If you could let us know, that would be really nice. So we could kind of work towards that application, right? So this is what's kind of happening next up. But to summarize, in a nutshell, my message is the following, right? Normalization for Fitch-style modal calculi can be achieved by constructing NBE models as instances of their possible world semantics. And the reason to do this is to avoid syntactic arguments because every system is different in a tiny little way. And the possible world semantics isolates all the modal differences to one specific parameter. And we're just sort of playing with that parameter here. But that's the end of my talk. Thank you.